we're talking about universal enveloping algebras of Lie algebras at the moment. Actually, I want to start off today with an important theorem, the Poincaré-Birkhoff-Witt theorem. So that's a bit of a mouthful, PBW for short. So this is totally general. G is any Lie algebra. And U of G is its universal enveloping algebra. So we defined that last time as the tensor algebra, so that's the free associative algebra on the vector space G, quotiented out by the two-sided ideal generated by x tensor y minus y tensor x minus the commutator xy for all vectors x and y in G viewed as a subspace, the degree 1 part of the tensor algebra. So in other words, we're trying to force the actual commutator given by xy minus yx to equal the Lie algebra commutator. And I think you observed already that this was in degree 2, whereas this here is in degree 1. Degree in the sense of the tensor algebra. But the tensor algebra is a graded algebra. It's the direct sum over all degrees, the dth tensor power of G. Okay, so that's the setup. Then PBW says, well, I think first of all it says that the canonical map I from G to U of G, which we had last time. Last time that was sending x to x bar. So that's just gotten by including G into the tensor algebra and then mapping the tensor algebra onto the quotient algebra U of G. So this map is actually injective. I didn't have that last time because it's part of the PBW theorem, just a little piece of it. So because of that, we can identify the Lie algebra G with a subspace of its universal enveloping algebra, and I'm going to do that from now on. Moreover, if you have some basis, let's call the basis maybe x sub I, as I runs over some index set. There's no need for me to assume even that the Lie algebra G is finite dimensional at this point. So this index set might be infinite. But if you've got some basis for G and some total order on the index set I, then the ordered monomials xi1, xin, this is for all n greater or equal to 0, I1 up to in in the index set in order. So I1 is less than or equal to in in that given total order. This is a basis for the universal enveloping algebra. So these guys here, they're often called ordered monomials. I think I usually call them PBW monomials. So you just need a basis and a total order on that basis, and then this PBW theorem gives you a basis for the universal enveloping algebra. Usually for us, of course, G is finite dimensional, and in that case it's just more convenient to index the basis just by the numbers 1 through n, where n is the dimension. And so this gives me the ordering totally in the first place, and then this PBW basis, in this notation you just write it as x1 to some power, x2 to some power, xn to some power, where m1 up to mn, then they're just some natural numbers. Okay, so that's the theorem. I'm not going to give you a totally complete proof, but I want to give you some fairly detailed comments about the proof. So I'm kind of going to skip the technical part. Yeah, let me motivate what's going on with something that you've probably seen before that's much easier, but it's such a good example that this is what you should really have in mind. So this is the first Weyl algebra. Let's call that A. So this is the free associative algebra on two generators with just the relation that xy minus yx minus 1 is 0. So xy minus yx, the commutator of x and y, is equal to 1 in this first Weyl algebra A. Okay, so this is the free associative algebra on two generators. So this has basis just monomials y to the j, x to the I, for I and j greater than or equal to 0. And this is just like a kind of a baby case of the PBW theorem we're about to prove for universal enveloping algebras of Lie algebras. But this baby case, the usual proof is rather easy. And so I can sketch this much more cheaply than I can sketch the proof for universal enveloping algebras. So the first observation is that these y to the j, x to the I, these ordered monomials, span A. That's easy because you see this relation says that if you ever have an x before a y, you can flip it around and it becomes an x after a y with a little cost. You get a little lower degree error term popping up whenever you go. But by induction on degree, it's easy to see that you can kind of straighten any monomial, not necessarily in order, to get the ordered monomial plus lower terms. And so that's the spanning. And then what you do is you define an action of A on the polynomial ring in one variable. In other words, you make this polynomial ring into a left A module. So y acts as multiplication and x acts as differentiation with respect to y. So to do that, you just have to check relations. And so you just have to check that these endomorphisms of the vector space C of y do indeed satisfy that relation, and that's just the product rule. You just have to note that for a polynomial f, the derivative of yf, it's y times the derivative of f plus f. And when you rearrange that, that's exactly, if x is this d by dy operator, that's exactly the relation defining the first Weyl algebra. And then you use this action to prove the linear independence of our spanning set here. Right? So you just act on some suitably chosen power of y in the polynomial algebra, and since you know that the monomials there are linearly independent, it's then quite easy to finish off the proof of this basis theorem for the first Weyl algebra. In fact, the first Weyl algebra A is what's called a filtered deformation of the polynomial algebra, so the free commutative algebra on two generators. Let me explain what these words mean. So I guess to start with, we should go back to this free associative algebra on two generators. Let's call that T. Actually, that's just a tensor algebra, right? If you take the two-dimensional vector space with basis x and y, then this associative algebra T, it's just a tensor algebra of that vector space. So it's a graded algebra because the tensor algebra is a graded algebra. So x and y are in degree 1, and those generate this graded associative algebra. But the ideal I that we're factoring out, this ideal generated by xy minus yx minus 1, this is not a homogeneous ideal, because it's got this mixture of degree 2, and look, this is actually degree 0 in here. So because it's not a homogeneous ideal, then the first Weyl algebra A is not a graded algebra quotient of the tensor algebra. All you can do then is actually get a filtration on the quotient A. It's not a graded algebra, it's merely filtered. So what does this mean? If you let A less than or equal to n be the image of the degree d graded pieces of the tensor algebra, so Td, as d goes from 0 all the way up to n. So this I'm going to call A less than or equal to n, right? So that's the image of everything of degree n and less in the tensor algebra. So the span of all monomials in x and y of degree n or less. And then this is exactly the structure of a filtration on this algebra. So let me write down what this satisfies, and you'll immediately see the definition of what filtered algebra is. We have that, so A less than or equal to 0, that's just the ground field sitting inside A, so the span of the identity element, and then that sits inside A less than or equal to 1, which sits inside A less than or equal to 2, and so on forever. So these are all subspaces nested. And if you take A less than or equal to m and you multiply with A less than or equal to n, that lands up in A less than or equal to m plus n, because that's just coming from the multiplication in the tensor algebra, which is a graded operation. Okay, so those properties are the definition of filtered algebra for our purposes. Whenever you have a filtered algebra, you can talk about its associated graded algebra. And that's denoted GRA. So that's a graded algebra. Maybe I use D for degree. Where the degree piece, by definition, it's A less than or equal to D quotiented out by the subspace A less than D. I think that notation is just the common sense thing, as you expect. The direct sum of all the... I should probably write A less than or equal to D minus 1, but that's a bit clumsy. Now, if you have any x in filtered degree n, and you let what I denote GRA sub n of x denote x modulo A less than n, so this is inside the degree n graded piece of the associated graded algebra, well then this GRA A, which so far is just a graded vector space, these sections give the pieces of that graded vector space, then in fact this is a graded algebra. With so I need to define the multiplication, right? So I'm going to tell you how to multiply something in degree n with something in degree m. What you do, that should be a y. What you do is you pick lifts x and y upstairs in the filtered algebra A, you multiply them together in A, and then you take the GRA n plus m, you push them back down again. So of course you have to check that this is well defined, because x and y are lifts of these elements in the associated graded in this subquotient. And the check that is well defined, well, it just boils down to the fact that the multiplication was a filtered multiplication. That property star there is what you need when you go through that check. It's otherwise unsurprising. Okay, so that's the general notion of a filtered algebra and its associated graded algebra. I guess the one trap to fall into is to think that there's a linear map from A to gra A, sending an element x to gra x. There's no such linear map. There's merely this collection of all of these linear maps called gra n, which go from A less than or equal to n to gra A n. So if you write gra as a function, as a linear map, there's no such thing. You're doing something wrong. Okay, back to our first Weyl algebra. The basis theorem that we've just established shows that this the degree n part of the associated graded has basis given by all of the y to the j, x to the i's with I plus j equals n. Maybe I should just write gra a sub n. And so here I should put gra n of that element in A less than or equal to n. Okay, so that follows immediately from the basis theorem for A that we just established. From that you can read off a basis for each of these filtered subspaces, these A less than or equal to n's, and then you see that indeed the ordered monomials of degree n, when you pass down to the degree n graded piece, give a basis downstairs. But this is actually just equal to gra 1y to the power j, gra 1x to the power I. Also, gra 1 of x and gra 1 of y commute in the associated graded. Remember the definition of multiplication in the associated graded right here. So what have you got to do to check that? You've just got to actually check that gra 2 of xy equals gra 2 of yx. That's that statement right there. And you see the relations that we've got mean that xy minus yx is actually in degree 0. So when you apply the linear map gra 2 to it, you just get 0 because gra 2 kills everything in degree 1 or less. So this means that there's an algebra homomorphism from the polynomial algebra now in two variables. And I'm sorry I'm using the same letters x and y here in the polynomial algebra as I was using in the first Weyl algebra. But I'm just abusing that notation a little bit, and I think what I'm about to write still makes good sense. So there's an algebra homomorphism just from the universal property of the polynomial algebra. It's the free commutative algebra on two generators. So this sends x to what's called gra 1 of x on the right hand side, and y to gra 1 of y. And let me see, our basis for the associated graded algebra, these guys here give a basis, so that just shows that this map is onto. In fact, the basis of monomials in the polynomial algebra goes to the basis of monomials in the associated graded algebra, so this isn't just an algebra homomorphism, it's an algebra isomorphism. So the associated graded of the first Weyl algebra is the polynomial algebra, and that is what it means to say that the first Weyl algebra is a filtered deformation of the polynomial algebra. So you see, kind of in the end, what's going on is, look, the relation that we imposed, xy minus yx minus 1, if we were defining the polynomial algebra, we would have just missed off that minus 1. We would have had that homogeneous relation forcing x and y to commute. And in our deformation, we've got this extra lower degree term sneaked in there. The proof that we've gone through, this proof of this basis, establishes that indeed, as your intuition might misleadingly tell you, it's not misleading in this case, and this filtered deformation is indeed a filtered deformation of the polynomial algebra. So take all that as kind of a warm-up for the story for the universal enveloping algebra of a Lie algebra, and it's very similar. So back to the PBW theorem for our universal enveloping algebra. So that's a basis theorem. To prove the PBW theorem, you have to go through the same steps as the proof for the first Weyl algebra. So the first observation is that the ordered monomials span the universal enveloping algebra. That's kind of clear. You see, if we go back to the defining relations, that defining relation right there is telling you that you can take any two Lie algebra elements in U of G and you can commute them modulo a degree 1 term, modulo a lower degree term. So it's saying you can take any monomial, and they certainly span because they span the tensor algebra. You can take any monomial and reorder it modulo lower terms. So by induction on degree, you get this spanning part. So then you have to come up with some representation. So for the first Weyl algebra, this was the module, just the polynomial algebra in Y, which we used. Now what you do is you make the symmetric algebra on the vector space G. You make this into a left U of G module. So what you have to do is you have to, so I'm not going to distinguish between elements of G or U of G or S of G. So this notation is again, I'm abusing notation a little bit because otherwise it really gets out of hand. So if you take a monomial in the symmetric algebra, right? So symmetric algebra, that's just polynomial algebra in our basis. So if you take a monomial in there, and then you act, so this is an element of G, this is an element of S of G. So we're trying to make the symmetric algebra into a left U of G module, which you remember is just the same as being a G module. As we discussed last time. So all I have to do is I have to define actions of the Lie algebra elements on monomials. So this is going to be just by left multiplication. Modulo lower degree terms. So I haven't told you, so it's equal to just the left multiplication plus some linear combination of monomials of strictly smaller degree. That's not enough to work this out uniquely, but together with this property, it actually is exactly equal to that left multiplication if it happens that I is less than or equal to all of those j's. So it turns out then there's actually a unique way to do this. Just following those two properties, there's actually a unique way to do it, given that you want the axiom of a module over a Lie algebra to be satisfied, right? So the commutator has to act as the commutator, if you like to say it that way. So this is the unpleasant step in the argument, and the one I'm going to totally skip. So it's all done by induction on degree, and it's just a little bit too technical for me to have any desire to go through it here. So once you've constructed that module, then you use this action to show the linear independence of the PBW monomial. So all you have to do for that is you just act on the identity element in the symmetric algebra, and that does your job. So that's my rather poor attempt to prove the PBW theorem for you. I think that's actually the right level of detail that you want to get the sense of this. You know, maybe it's worth mentioning that there's even an axiomatization of this type of argument, so that it's actually very useful for all sorts of associative algebras defined by generators and relations, not just our universal enveloping algebras. And this is called Bergmann's diamond lemma. So if you've never come across that, that's well worth looking it up. That gives you a kind of formal axiomatic framework, and it tells you exactly what you have to check in order to, for the kind of obvious straightening algorithm to straighten all monomials into ordered monomials, for the ordered monomials at the end to form a basis. There's a precise bunch of ambiguities that you have to check in order to apply Bergmann diamond lemma. And it happens that when you apply it to the case of a universal enveloping algebra, you know, it's one of the very first examples in Bergmann's paper, actually. There's really only one check that you have to do. So if you're willing to appeal to that lemma, then the proof becomes much tidier. But of course, then you have to go and prove Bergmann's diamond lemma in greater generality. Okay, so that's a rough idea. And in fact, the universal enveloping algebra is a filtered deformation of the symmetric algebra. So having talked about this language for the first Weyl algebra, that this is in place now. So of course, it's a filtered algebra, as it's a quotient of the tensor algebra, which is a graded algebra. So the degree n filtered piece will be the image of, just like we did before, of the degree d graded pieces of the tensor algebra for all d less than or equal to n. So that's the filtration on the universal enveloping algebra. And I claim that the associated graded algebra is the symmetric algebra on the vector space G. And so this actually follows from the PBW theorem. Indeed, it's equivalent to the PBW theorem that we just proved, or that we just outlined how you would prove if you could be diligent enough to go through that delicate induction. So the PBW basis that as I stated it above, implies that the degree n piece of the associated graded algebra, it has basis coming from the ordered PBW monomials, xi1 up to in, for I1 less than equal to in in our order, are the gra n's of those guys. And just like for the first Weyl algebra, those are the same as gra 1 xi1 multiplied in the associated graded algebra gra 1 xin. Also, gra u of g is commutative, because if you take the bracket of gra 1 of x and gra 1 of y for some Lie algebra elements x and y, that's the same as gra 2 of xy minus yx, which by the defining relation, that's gra 2 of the Lie algebra element xy, which is in degree 1. so that's simply 0, right? So that's the check of commutativity. So, by the universal property of symmetric algebra, you get an algebra homomorphism from S of G to grow U of G, sending an element X in the generating vector space G to grow 1 of X in here. So there's such a map because this associated gradient is commutative. This map is actually onto, because our PBW basis implies that these degree 1 elements generate the universal generate this associated graded algebra, and in fact these ordered monomials here, they're just the image of the usual basis for the symmetric algebra, so it's actually an isomorphism. And there is the statement that the universal enveloping algebra is a filtered deformation of the symmetric algebra on the vector space G. So that's another way of thinking about the PBW theorem. Okay, so that's kind of useful for us. So in particular, this means that now I'm always just identifying the Lie algebra G as a subspace of the universal enveloping algebra. And then we really, this universal enveloping algebra, it's an associative algebra, and it's the kind of largest associative algebra that can be generated by the Lie algebra G, so that the Lie bracket is equal to the commutator in that associative algebra. Okay, so at the end last time, I gave you the 3 basic examples of Hopf algebra in mathematics, the first 3 that you come upon. So remember, Hopf algebra, it's an associative algebra together with a co-multiplication, a co-unit, and an antipode. And I have written down the diagrams that are the axioms of these guys. So example 1 was the group algebra of a finite group. Example 2 was the coordinate algebra of an algebraic group. And example 3 is the universal enveloping algebra of a Lie algebra. Okay, so that was where we were. Those are not very straight lines. Let's try that again. So in case 1, the co-multiplication was defined on a group element. Delta of G is G tensor G for G and G. So elements with this of a Hopf algebra with this property, by the way, are called group-like elements. Elements where delta of the element is just the element tensored itself. Those are the group-like elements of a Hopf algebra. And the co-unit on a group element is 1, and the antipode on a group element is G inverse. Again, G and G. For the coordinate algebra of an algebraic group, the co-multiplication was just dual the comorphism of the multiplication on the algebraic group itself. The co-unit was just evaluation at the identity element, and the antipode was the comorphism of the group inversion map. And finally, for the universal enveloping algebra case, the co-multiplication on a Lie algebra element was x tensor 1 plus 1 tensor x. The co-unit on x was 0, and the antipode on x was minus x. So all this is for x in the Lie algebra, And now you see I'm thinking of the Lie algebra as sitting inside the universal enveloping algebra. It generates that as an associative algebra. And I think I didn't go through the details last time, and I'm not going to do it here, but just remember that you need to use the universal property of the universal enveloping algebra to see that these extend appropriately. Remember, delta and epsilon are both algebra homomorphisms, and the antipode S is an algebra anti-homomorphism. But just using the universal property of universal enveloping algebra, you can check what you need to do to see that this is enough to define well-defined such maps on all of U of G. So I think it's helpful to kind of think of this that the universal enveloping algebra is to the Lie algebra G, just as the coordinate algebra of a finite group is to G for a finite group G. When you have a finite group, you look at the category rep G, which is modules, so finite dimensional representations. It's the same thing as finite dimensional left modules over the group algebra. And in exactly the same way, for a Lie algebra, rep G, finite dimensional representations of G, that category, it's just exactly the same as finite dimensional left modules over the universal enveloping algebra. So this is, of course, desirable because the general theory of modules over a ring is something we're familiar with, and this just reveals that these categories of representations of finite groups or Lie algebras are indeed just module categories over associative algebras, the group algebra or the universal enveloping algebra. But for an algebraic group, it was a little bit different, right? The category of representations, finite dimensional representations of an algebraic group, is actually the category of finite dimensional comodules over the coordinate algebra. So you need this notion of comodule when studying representations of algebraic groups. And in this case, you actually have to develop this new theory of comodules over co-algebras, and you can't appeal to facts that you know about modules over rings in this world. So representations of the algebraic group is a little bit less of a familiar story. Okay, so the three basic examples of Hopf algebra. We have them all appearing in front of us here. So why is this important? So let's just be a little bit in general. Let's say A is a Hopf algebra with a co-multiplication delta, co-unit epsilon from A to the ground field, and antipode S from A to A. Then the category of finite dimensional left A modules is what's called a tensor category. So what does tensor category mean? It means it's abelian. There's a tensor product operation. There's a duality operation, star, and there's a unit object. Called trivial modules is what I usually say in representation theory. So that's just the ground field that you're working over, but there's a kind of distinguished way to make the ground field into a left A module. So how did these all come about? These are all kind of fairly straightforward. So of course it's a modules over a ring, so it's an abelian category. So what's the tensor structure? So if you have V and W A modules, then V tensor W, that means just the tensor product of those vector spaces over the field. Everything is over that field, so tensor means tensor over that field. This is, of course, an A tensor A module. Just totally obviously, pure tensor in A tensor A acts on vector V tensor W, just A acts on the V and the B acts on the W. So it's an A module via the homomorphism delta from A to A tensor A. You can pull back the natural action of A tensor A on V tensor W through this algebra homomorphism to get an action of A on V tensor W. So that's the tensor. The duality sends a vector space V to V star, which is just the linear dual. So you need to be able to define an action to make that into a left module to get this duality. So if you have an F in V star, an A in A, you need to be able to define that left action of A on F. So to do that, I need to define what function it is on a vector V, and it's just F of the antipode of A, V. This, for me, is always the most convincing way to remember that the antipode should be an anti-homomorphism, so that this indeed turns a left module into a left module. And then finally, the trivial module, K, has action defined by, so the way A acts on 1 in there, it's just the co-unit of A times 1. Okay, so in other words, this co-unit, this is the representation corresponding to the trivial module, this distinguished one-dimensional representation. There's an awful lot more I should say about tensor categories, but I think I'm not going to do it because it's not going to be super important for our immediate needs. But maybe I should add just one word. It's not just and maybe I'll make it in a different color, like red, because I need to add one word somewhere else. Right up here. There we go. I think I can fit it in now. Not quite. Okay. I need so you need A not just to be a Hopf algebra, but to be what's called a co-commutative Hopf algebra, and then the category of finite dimensional left A modules becomes a symmetric tensor category. What that means is that V tensor W, W tensor V, this map sending pure tensor little v tensor little w to the flip little w tensor little v, is actually an A module isomorphism. That's what the word symmetric means, and I guess maybe I should make that in red as well, because this is all just in this with this extra assumption that the co-algebra is co-commutative. What does co-commutative mean in there? That means that if you go from A to A tensor A, or you flip with delta and delta, and then flip is the tensor flip, as always, so that diagram commutes. So back to the three main examples. So the coordinate algebra of a finite group, look, it's co-commutative because that's symmetric when you flip. The universal enveloping algebra of a Lie algebra, that's a co-commutative Hopf algebra because if you flip the tensors, well, you get the same thing. That's the co-commutativity. So these two categories, representations of a finite group or representations of a Lie algebra, they are both examples of symmetric tensor categories because they're modules over co-commutative Hopf algebras. For the representations of an algebraic group, the story is a little bit different, right? So this time it's co-modules, and you have to use the algebra structure to give you a tensor structure on the category of co-modules over this co-algebra. And this is again actually a symmetric tensor category because the algebra structure is commutative, because the coordinate algebra is a commutative Hopf algebra. So let me just note here that all three categories are symmetric tensor categories. And so that's why this Hopf algebra structure is important. It gives you this tensor product and this duality and this trivial module. Okay, this is all good stuff. So let's, I still want to say a few more things today, I must say. Let's see if I can just finish up in the next maybe 6 or 7 minutes I'm going to need. So if A is a Hopf algebra, you can always make A star the linear dual of that vector space. It's always an algebra. What do you need? You need an algebra multiplication. So you need a linear map from A star tensor A star to A star. But you see, that embeds in the dual of A tensor A canonically, and you have a distinguished map from A tensor A star to A star in here, the dual map to the co-multiplication delta on A gives you that map. And because the co-multiplication is co-associative, this produces a multiplication on the vector space A star, which is associative. I should explain why there's a unit. That's the dual of the co-unit on A. But that's enough said. But A star is not necessarily a co-algebra or Hopf algebra. In a natural way. So the problem here, you see, if you try and do this, so you make A star into an algebra by dualizing the co-algebra structure on A. You think you might be able to make A star into a co-algebra by dualizing the algebra structure on A. But if you want to do that, what are you after? You're after a co-multiplication. And the dual of the multiplication certainly gives you a nice candidate, a linear map from A star to A tensor A star. But the problem is that might be, that contains A star tensor A star, but in general, the image of this map, the dual of the multiplication on A, needn't be in the subspace A star tensor A star naturally embedded into A tensor A star. So you don't get a co-multiplication from kind of the construction that you obviously hope that you could do. If A is finite dimensional, no worries. Then that's actually an isomorphism by dimension. And so you see in this case that the dual of a finite dimensional Hopf algebra is again a Hopf algebra via this construction. Okay, so example. The coordinate algebra of a finite group. Then the dual of that Hopf algebra is again a Hopf algebra. And in fact, this is just exactly the same thing as the coordinate algebra. You see, finite groups, they're also algebraic groups, right? So you have this Hopf algebra that's the coordinate algebra of that finite group, thought of as an algebraic group now. And in fact, the coordinate algebra is exactly the dual of the group algebra in that case. And this is even as Hopf algebras. So you see in this case why the notation rep G for a finite group, finite dimensional KG modules, and rep G for an algebraic group, comodules over the coordinate algebra, why they match up under this construction. Modules over KG and comodules over the dual just become identified. So this is left KG modules and right K of G comodules. They turn out to just be the same data, so these are isomorphic categories. And so in the case of a finite group, which is also an algebraic group, the notation rep G, it's just the same tensor category in both cases. So the final thing to be said is, what if you have a connected algebraic group? Then you can look at the coordinate algebra. That's a Hopf algebra. You can look at the dual. This is an algebra, but it's kind of too big to be a co-algebra or Hopf algebra. So that's the issue. You can't dualize an algebra to get a co-algebra without some unless it's finite dimensional. So now you consider something called dist G. So this is the algebra of distributions of the algebraic group G. So by definition, that's all elements of the linear dual, which is an algebra, such that theta kills me to the power n plus 1 for all sufficiently large n. And here this me, that's the kernel of evaluation at E, that's the maximal ideal of the coordinate algebra corresponding to the point E in the group. Okay, so we're starting from an algebraic group here. You have the maximal ideal corresponding to the identity element. And if you don't look at the whole linear dual, you look at this subspace called dist G, all functions from K of G to the field, which kills sufficiently large powers of this maximal ideal. So maybe another way of thinking about this, it's the union of K of G quotiented out by the n plus 1th power dual. That's this algebra of distribution. So it sits inside this algebra K of G star. It's a subalgebra. In fact, it's a filtered algebra naturally, with the filter degree n piece being exactly that space that I just wrote down, it's even a Hopf algebra with co-multiplication that's due to the multiplication on K of G. So this construction fails in general on A star, but if you restrict to this subspace dis G of A star, then it turns out that when you apply this dual to multiplication to that, you do end up in dis G tensor dis G when you do this. So you do get a Hopf algebra structure on this algebra of distribution. So this is sort of a reasonable finite way of taking the dual of the coordinate algebra and getting a Hopf algebra out. This makes sense over any field of any characteristic, but let me just finish out, since I've run on a little bit. Let me just write a little tiny sentence. In characteristic 0, it turns out that dis G is actually isomorphic to this universal enveloping algebra as Hopf algebras. So I'm going to be just a little bit incomplete here, I think. Remember that the Lie algebra, that was this space of point derivations, and I think it's quite an easy exercise to see that Lie algebra of point derivations is the same as the dual space of this maximal ideal modulo its square, and you can sit this inside dist G in an obvious way. This is these are functions which kill the square of the maximal ideal, and you get a Lie algebra homomorphism from G to dis G from this. So you have to check that indeed it's a Lie algebra homomorphism, and that induces, by the universal property of universal enveloping algebra, that induces this map here, and then you have to show that it's an isomorphism, and the isomorphism here requires characteristic 0. So that's kind of gives you a different way of thinking about this Lie algebra and this universal enveloping algebra, and you can use that. In fact, you can use that as the definition of the Lie algebra. So first construct universal enveloping algebra, and then you see a different way of getting hold of the Lie bracket on the Lie algebra sitting inside there. Okay, but I've run on a little bit today, so let me stop.